Hello, my name is Lijo Wu. I'm a PhD candidate from TU Delft. So today I will be presenting this work, Impact of Magnetic Coupling and Density on STT-MRAM Performance. This work was done in collaboration with our partner IMEC. STT-MRAM is not a myth anymore, it's becoming a reality. So probably in a few years you would find STT-MRAM chips in your smartphones, in your laptops. At the moment, Spin Technology is the only manufacturer which provides commercial products of STT-MRAMs. And this chip is 1 gigabits, and for high-end SSDs, the retention time is larger than 10 years at 85 degrees Celsius. The endurance is 10 to the power of 11, which is high enough for storage applications. And Intel also demonstrated its STT-MRAM solution last year for L4 caches. And read-write performance is very impressive. The retention time, however, is a bit lower, just 1 second at 110 degree. The endurance is also very good. And apart from these two companies, a lot of foundries across the globe are catching up, including Samsung, TSMC, Global Foundries. These are just the first generation STT-MRAM chips, and of course there's still a lot of space to improve the design. And as a final goal, we need our STT-MRAM chips to be high density, high performance, and reliable at the same time. Among all challenges facing STT-MRAMs, a magnetic field interference is one of them. We know that STT-MRAMs are very vulnerable to external fields. Imagine we have a STT-MRAM chip and someone wants to attack our data, and he just needs to put a big magnet near our device, then maybe the data is gone. So how do we protect our data? For example, Global Foundry proposed to add an in-package magnetic shield to enhance the magnetic immunity. In this way, we can protect our STM chip against external fields. Then how do we deal with the internal magnetic fields generated from the inside of device? Because STT-MRAM device consists of dozens of ferromagnetic layers, and the bad news is that each layer generates a stray field, as you can see with this cartoon image here. And the second bad news is that this stray field generated by each device also has an impact on the neighboring cells. This leads to intra-cell magnetic coupling. So how do we model intra-cell and inter-cell magnetic coupling, and how do we evaluate their impacts on the performance of STT-MRAM? This is the topic of This is the outline of my presentation today. So first of all, I will briefly introduce the basics of STT-MRAM technology, because not everyone is familiar with this topic. Then I will show you guys how we measure the inter-cell magnetic coupling for isolated devices. And then I will explain how we model the inter-cell magnetic coupling. When we have a model, then we fit the modeling results to the measurement data to make them match. And when we have a good model for inter-cell magnetic coupling, we extrapolated this model from one single device to a memory array to investigate the inter-cell magnetic coupling, the magnetic coupling between memory cells. Then when we have a good model for both inter-cell and the inter-cell magnetic coupling, we evaluate the impacts of magnetic coupling on STT-MRAM performance. And in the end of this presentation, I will draw some conclusions. So first, background. Here you see a simplified MTJ stack. From top to down, the first layer is called free layer, where the magnetization can be either pointing up or pointing down. And the second layer is called tunnel barrier, which is a dielectric layer. And the third layer is called reference layer. As you can tell from its name, the mechanization in this layer provides a reference to that of the free layer. And the bottom layer is called the hard layer, which is used to strongly pin the mechanization in the reference layer. And the reference layer and hard layer form a synthetic anti-ferromagnetic structure. And this self structure is widely used in MTG designs in the community. Of course, in reality, the device structure is much more complicated. However, to simplify this problem, you can still consider this device is composed of these four basic layers. And as this reference layer and hard layers are both ferromagnetic layers, they unfortunately generate stray fields acting on the free layer. And this C letter in the superscript represents the out of plane components. Then this device has two bistable states. When the mechanization in the free layer is parallel to that in the reference layer, then it shows a parallel state, which is low resistance. And when the two mechanizations are anti-parallel, the device has relatively high resistance. So here I want to highlight a key term, which is the thermal stability. This term represents how stable these two states are against thermal fluctuation. And this thermal stability has something to do with the retention time. The larger the thermal stability, the longer the retention time. We have learned a little bit about the device structure and its binary states. As a memory element, we need to write dates into the device and read date out of it. For MTJ devices, there are basically two write methods. The first one is using electrical current. Let's first take a look at an example. For example, write zero operation on an MTG with the initial states 1, in other words, anti-parallel states. We apply a current flowing from the free layer to the hard layer, and when, of course, the electrons flow in the opposite direction, and when the write current is larger than the critical switching current, then the mechanization in the free layer flips to the opposite direction. This is induced by the spin transfer torque provided by the write current. And to switch to the opposite direction, the switching process takes some time. Therefore, the switching time is a very critical parameter to the write operation. And in addition to using electrical current, we can also use an external magnetic field to write the data into the device. So the same operation, the same initial states, and we apply external fields on the device. And when the external field reaches at the threshold point, here the threshold point is defined as the critical switching field, then the mechanization in the free layer again switch to the other direction, and the direction of the mechanization now aligns with the direction of external fields. So here I want to highlight another critical parameter, which is called device coercivity. This term is defined as the reverse field to drive the mechanization to zero. And because of the existence of stray field at the free layer, the critical switching field may not necessarily be equal to the coercivity of a device. Alright, so next let's take a look at the measurement setup and the measurement results on real fabricated devices at IMEC. We load the wafers and tests into the measurement tool, and in a small chamber of this tool, ramped perpendicular field is applied to each device and test. And the timing of this external field is shown here in the second figure. Following each field point, we apply a read operation with a very small voltage to read back the state of the device. After setting up the measurement, then we leave the tool running for a couple of hours. Then we go to the lab to fetch the measurement data. Ideally, if there's no street field as a field there, we expect the RH loop to be symmetric at the central vertical line, as here you can see in the third figure. When we get the measurement data, we use Python to plot the data. Here I show you an example of the measured RH loop. You can see that this loop is not symmetric, it shifts to the positive side. And from this RH loop, we can also extract the device code safety using this equation. We can also extract the offset fields. And the intra-cell street field is equal to the offset field, but the sign is reversed. So here we need to note that if the intra-cell street field is larger than the code safety of the device, bistable states no longer exist. We also found that the intra-cell street field depends on the size of the device. As a common practice, we use electrical critical diameter to represent the size. So here I show you the measurement results. You can see how the intra-cell street field scales with the device size. As the ECD decreases, the intra-cell street field increases in absolute value. Here the points represents measurement data, and the solid curve is the simulation results, which I will show you later. Next, I will show you how we model the intra-cell magnetic coupling. We use the measurement data to calibrate and optimize this model. Then we move on to the modeling of inter-cell magnetic coupling. We use a bound current theory to model a ferromagnet as a current loop because we want to model the intra-cell street field at the field there. Therefore, we only consider the reference layer and the hard layer here. In this theory, it assumes that each ferromagnet is uniformly magnetized. For example, the reference layer generates a street field which is identical to the field produced by the bound current loop. So what is the bound current? If we dive into the microscopic space of reference layer, the entire ferromagnetic moment is actually composed of countless tiny dipoles, and each dipole can be represented by a small current loop. And as you can see here, and for all these internal current loops cancel each other. However, for those lying at the edge of the ferromagnets, they have no neighbors to cancel out each other. Therefore, the macroscopic effect is that there's a bond current flowing around these ferromagnets, but this is imaginary. This bond current is not real current. So when we calculate this bond current magnitude, then we can use Biot-Savart law to calculate the field generated by this current loop at any point in the space. Then the same modeling flow applies to the hard layer, and then we add up these two components. It becomes the inter-cell magnetic coupling at the field there. For more modeling details, please refer to my paper and also the references of my paper. On these slides, I show you the modeling results. This 3D plot shows what the field look like in the space around the device. The device ECD is 55 nanometer, and if we cut the device vertically, then we get 2D plots, right? And we only show the outer plane components of the field here. because the in-plane component is very marginal and has negligible impacts. And as we can see here, three field distribution across the free there is not uniform, is inhomogeneous, and the field at the edge is much smaller than at the center, and the polarity is even the opposite to that in the center. Now we've got a good model for a single memory cell, but STT-MRAMs always come in a memory array. Therefore, we need to extend this model to a memory array to investigate the inter-cell magnetic coupling as well. To this end, we built up a 3x3 memory array, and we can consider the cell in the center as a victim cell, and all the other 8 neighboring cells are grasses. And because the distance of these 8 cells to the center cell are different, therefore we divide them into 2 groups. So the first group is the direct neighbors, because these 4 cells are in symmetric positions, and we encode them together from 0 to 3. And the second group is called direct neighbors, and these 4 neighbors are also in symmetric positions with the same distance to the victim cell. And we use NP sub 8 to denote the neighborhood pattern in 8 aggressor cells. And because each cell can store cell either 0 or 1, therefore the neighborhood pattern can be a value between 0 and 255. And to calculate the intercell straight field from these 8 neighboring cells at cell 8, we need to sum up all the fields from neighboring cells, and for each neighboring cells, we have to count the field generated from all 3 ferromagnetic layers, which are the hard layer, reference layer, and free layer. And for a given pitch, the field from the hard layer and reference layer are always fixed, because after manufacturing the chips, the magnetization in these 2 layers are always fixed. However, the field generated from the free layer changes with the date pattern. Why? Because the magnetization in free layer always changes with the data stored in the cell. We know that there are 8 aggressor cells, therefore there are 2 to the 8 different data patterns, but all direct neighbors are in symmetric positions, and the same for diagonal neighbors. So obviously some data patterns have the same intercell straight values. To get rid of the redundant values, we just put the number of ones in direct neighbors on the axis and the number of ones in diagonal neighbors on the y-axis, and we put the intercell straight values on the z-axis. In this way, you can see all possible values for the intercell straight fields while getting rid of all redundant values. In this simulation, we set ECD to 55 nanometer and pitch at 90 nanometer. These values are adopted from SK Hynix's STT-MRAM design. And you can see that when all neighboring cells are in state 0, then the intercell straight field reaches the lowest value. And as the number of ones in direct neighbors increases, the intercell straight field also increases, and the same for the number of ones in diagonal neighbors. And when all neighboring cells are in state 1, In other words, NP sub 8 is equal to 255. Then the inter-cell sweep field reaches the peak. And here you can clearly see there is a big variation in the inter-cell sweep field. If this variation exceeds certain point, this may create a big problem. So to evaluate the inter-cell magnetic coupling strength, the psi value changes with MTJ size and array pitch. In our simulations, we set the minimum pitch at 1.5 times ECD, so the minimum pitch mainly limited by the etching technologies. We set the maximum pitch at 200 nanometer, which is used by both Intel and Samsung. Now let's take a look at the figure. So and you can see that at pitch 200 nanometer, the psi value is almost zero, meaning that there's almost no inter-cell magnetic coupling effects. But as the pitch goes down, in other words, you push the memory cells closer to each other, then the psi value increases gradually, and when it reaches at a threshold point, it goes up exponentially. And we consider this threshold point as a tipping point where the array density is maximized with negligible inter-cell magnetic coupling effects. So in our design, this threshold point corresponds to 2%. Maybe different designs have a slightly different psi values, but we can see below this 2% is a safe design space, and later on I will show you the impact of magnetic coupling on device performance at this specific point. Alright, at this moment we know that magnetic coupling has two parts. First, intra-cell magnetic coupling, which means the stray field from the device itself. And the second part is inter-cell magnetic coupling, which means the stray field from neighboring cells. And the overall stray field depends on three factors. First, ECD, which means the size of the device. Second, the pitch. This is the density of MRAM array. The third one is NP sub 8, which means the data pattern in neighborhood. And then we will use this model to evaluate the impacts on the STT-MRAM performance. First, we will see how the magnetic coupling impacts the switching characteristics. So basically two parameters, the critical switching current and the switching time. Then later on, we will also see the impacts on the thermal stability. Thermalability, as we said, is a key parameter determining the retention time of STT-MRAM. We use the microspin model to calculate the critical switching current. The equations of this model can be found in this reference. And we did a simulation for MTJ devices with ECD 35 nanometer. Let's take a look at the simulation results. So the dashed line in the middle of this figure represents the critical switching current, where there's no stray field at the free layer. Now let's take into account the intra-cell stray fields, and we see that the stray fields introduce a static shift in the critical switching current, making one switching direction approximately 7% up and the other switching direction 7% down below the intrinsic critical switching current. And now let's take into account both intra-cell magnetic coupling and the inter-cell magnetic coupling, and we see that the inter-cell stray field introduces a dependency of the critical switching current on the array pitch and the data pattern in the neighborhood. So you can also see that when the pitch is larger than 80 nanometer, translated to a psi smaller than 2%, and you can see the variation is very marginal. In terms of switching time, we use STT switching model to calculate the average switching time. These equations can be found in the reference below. We did a simulation where we set ECD to 35 nanometer and pitch 3 times the ECD, and we will show you the simulation results for AP to P switching as an example. So in this figure, you see on the x-axis the applied voltage on the device, and on the y-axis is the AP to P switching time as a result. If we compare the dashed line to the colored lines, we see that the intra-cell stray field leads to an increase in the switching time up to 40%. We can also observe that the larger the voltage, the smaller the impact on the switching time. And at this specific pitch value, we calculate that the psi value is 1%. And if we compare the two, the red curve with the blue curve, they are pretty much overlapped, which means that the neighborhood pattern has negligible impact on the switching time, simply because the pitch now is very large. So what if the pitch gets smaller? Now let's narrow the pitch from 3 ECD to 2 ECD, and we can see that the psi value increases to 2%. If we compare these two figures, we can barely see anything, which indicates that the neighborhood pattern has negligible impact on the switching time. In other words, when the psi is at 2%, the magnetic coupling effect has negligible impact on the switching time. Now let's keep decreasing the pitch from 2 ECD to 1.5 ECD. So just 0.5 ECD decrease. Now we see that the psi value increased dramatically to 7%. And if we compare these two figures, and we can see that when psi is at 7%, the blue curve is a bit far away from the red curve now, especially when the applied voltage is a bit small. For example, when the applied voltage at a device is 0.72 volts, the switching time when all neighbor cells are all in state 1 is 4 nanoseconds slower than the switching time when all neighboring cells in state 0. Now let's take a look at the impact of magnetic coupling on the thermal stability. Recall that to STT-MRAM, the thermal stability is proportional to the retention time. So we did a simulation, we set the ECD to 35 nanometer and pitch at 2 times ECD, where the psi value is approximately 2%. So we plotted the thermal stability versus operating temperature with respect to different magnetic coupling settings. And we can see that the intra-cell stray field introduces a static shift in the thermal stability, making the thermal stability in AP state approximately 30% higher than that in P state. In other words, AP state is much stable than P state, making P state have a shorter retention time. And we can also see that the worst case thermal stability occurs when the victim cell is in P states and all neighboring cells are also in P states. Now let's just focus on the worst case thermal stability, and we also plotted the worst case thermal stability versus operating temperature with respect to different pitches, and we can observe that the thermal stability is much more sensitive to temperature than to pitch. If we compare the curves, the 3 curves in the right figure, and we can see that as the pitch goes down, there is marginal degradation in the worst case thermability. Alright, some conclusions for this work. First, we conclude that magnetic coupling, including both intra-cell and inter-cell, is a critical design constraint for high-density STT-MRAMs. It has two parts, the intra-cell part and inter-cell part. In terms of the intra-cell magnetic coupling, it leads to a significant static bifurcation in the switching characteristics and retention for the two switching directions. But this can be minimized by further device innovation, and it can also be exploited to compensate the circuit level asymmetry. In terms of intercell magnetic coupling, we saw that the denser the memory array, the stronger the magnetic coupling effects. To quantitatively evaluate the intercell magnetic coupling strength, we proposed in this work the intercell magnetic coupling factor psi. Psi is defined as the maximum variation in the intercell magnetic straight field divided by the coercivity of the device. And we suggested that when psi is at 2%, it maximizes the array density with negligible impact on the STT-MRAM performance. We also observed a marginal degradation on retention time at this pitch. That's all I've got. Thank you very much. I don't know how the conference organized the Q&A session at this moment, but as an alternative solution, you can send me your questions via email. So please feel free to contact me if you are interested in this work. It's a pity that we cannot attend this conference physically because of the outbreak of coronavirus. We wish all of you a healthy life and stay at home, stay safe. Thank you very much.